So we have looked at a bunch of techniques for solving differential equations. We saw how it's useful to work out the solution for the homogeneous equation, and then if you can find a particular solution for the full inhomogeneous equation, we can put these two together to get the full general solution for an inhomogeneous differential equation. And then we looked at special techniques for special kinds of problems and so on. So in this lecture we will look at some applications, right? So the core applications in of this kind of differential equation is in the context of mechanical systems, but completely analogous equations also hold in electrical circuit style systems, right? So we will just look at the mechanical problem, and the corresponding circuit problem is something that you can work out as either homework or it's really the same differential equation. You can look it up. Okay, so we start with something extremely familiar, very simple. So it's namely the a mass connected to a spring. So you have a mass m which is connected to spring with spring constant k, and so the differential equation which comes out is simply m times d squared x by dt squared plus k times x is equal to 0, right? So if it's at equilibrium, then there is no force, and then the particle will be at rest. But if it is moved by an amount x, then there is this restoring force, and so it's so we have this differential equation which we have seen since high school days. So then it's useful to non-dimensionalize this, to introduce this quantity omega, which is equal to square root of k by m, and so then our differential equation takes this form. And although we know the solution, it is useful to work this out from the principles that we have laid down. So we have a differential equation which is second order. It's a linear homogeneous differential equation, very simple differential equation. We know exactly how to solve it. So we start by writing it down as d squared plus omega squared acting on x is equal to 0. And now the left hand side is a quadratic form, right? So whose roots, the auxiliary equation has roots I omega and minus I omega. So we can factor the left hand side and rewrite it as d plus I omega times d minus I omega acting on x is equal to 0, from which immediately we are able to write down the general solution, which is just x is equal to a times e to the I omega t plus b times e to the minus I omega t. So equivalently we could have written this as cosine omega t and sine omega t, the linear combination of cosine omega t and sine omega t, whose coefficients you can work out in terms of a and b, right? It's all very familiar. Or equivalently we could have also thought of this as cosine of omega t plus some phase times an appropriate amplitude, right? So this is something we are familiar with. Now if we introduce some damping into our problem. So you have a damping force which is a frictional force which comes in if your medium has some viscosity associated with it. So the faster your particle is moving, the greater is this frictional force. And so the simplest assumption is that your viscous force is proportional to the speed, right, and in a direction opposite to the direction of motion. And it's if you assume that it's proportional to the velocity or the speed, so that the differential equation becomes m times d squared x by dt squared plus L times dx by dt plus kx is equal to 0, right? So if you don't have L, then it's just the earlier differential equation which we have already seen. Now it's useful to introduce these quantities omega squared and 2b, right? So it's convenient to think of this as 2b, for convenience as well as convention. So let's just use 2b is equal to L over m, right? So we can pull out this m throughout, and then we can rewrite this differential equation as d squared x by dt squared plus 2b dx by dt plus omega squared x equal to 0. So now once again it's a differential equation of a familiar type, right? So we have worked out the solution for more difficult problems than this. So here it's a homogeneous differential equation. On the right hand side is 0. So all we need to do is factor the left hand side. So we have d squared plus 2bd plus omega squared equal to 0. That's the auxiliary equation with roots minus b plus or minus square root of b squared minus omega squared, right? So the nature of this solution will be determined by what kind of roots you have, right? We have seen that there are 3 different kinds of roots possible. One of them will give you what is called underdamped motion, and it's oscillatory in nature, right? So it comes about when b squared is less than omega squared. So if b squared is less than omega squared, so then you have an imaginary component. So the roots are complex, and the 2 roots have to be conjugate to each other. So you have a pair of complex conjugates as the roots of this quadratic equation, and so the roots of the differential equation are simply given by this solution. So you have a sine beta t plus b cos beta t, the whole thing multiplied by e to the minus bt, right? So we could have written it in a different manner, but here it's transparent to pull out this factor e to the minus bt, right? So b is real. Now since omega squared minus beta squared is greater than 0, so beta is also completely well defined. It's square root of a positive number, and so you have a is unknown, b is unknown. It's a free constant, and there are 2 of these because it's a second order differential equation. And then you have this b e to the minus b is this is where the damping is coming in. So the more the damping, there is a decay in your the time evolution of your position. This so damping leads to decay, but there is also this oscillatory aspect, right? So there are these 2 forces in nature. One is, if there were no damping, of course, you have this is a simple harmonic oscillator which will perform oscillations about the mean, and so that part is still in here because damping is not so large. You see, that's what this b squared less than omega squared simply means. The damping is present, but it's not the dominant force. So in fact, so the the oscillatory aspect of the motion is still retained, right? So but it's also damped though, right? So no matter how small b is, as long as it's not 0, there is going to be a decay in the amplitude. So there is going to be oscillatory motion, but it is damped, and so it's so there is a periodicity to this kind of motion because of the oscillatory nature, although it's not really periodic in the sense that the position does not come back to exactly where it started every time period. It's still useful to think of to define the notion of a time period as the interval between 2 successive peak displacements, right? So, and that is given by simply 2 pi divided by square root of omega squared minus b squared. One should be careful about how one interprets this. Here it's it's completely well defined as the time interval between 2 successive peaks of your motion, right? Although it's not periodic motion strictly speaking. Okay, so let's plot it and see what it looks like. So if I plot this, so this is what it looks like, right? So this is so now you see that the time interval that elapses between your particle going from one peak to another is the same as a time interval that elapses for it to go from this peak to the next peak, although it never really comes back to where it started, right? So it is in that sense that it's not periodic, but there is a oscillatory aspect to it. There is something which repeats, and that has a very well defined period associated with it. Okay, so this is something that we are sort of familiar with, but it's useful to review it with all the machinery that we have developed. So then there is this second case, which is called critically damped motion. When if you think about increasing the damping, if you keep on cranking up the damping, there comes a critical value of the damping at which the roots become equal, and so the general solution now is a plus bt times e to the minus bt. So the damping is so large now that oscillations are not possible, right? So but this is a critical damping, which means that oscillations are absent, but only just, right? If the damping were reduced even by the smallest amount, then the system will again show oscillations, right? So depending on the initial conditions, there are three possibilities. So one is if you so I'll show you you know, qualitative aspects. So one is your system may just keep on decaying. So the equilibrium position uh, is never attained in the middle of its journey. It will eventually just die down to zero, but it's monotonically decreasing. There is no peak or anything of that kind, and it will just monotonically approach the equilibrium position as at time going to infinity, right? So then there is a second possibility, which is that it tends to go up before falling down, right? So this is so there is a characteristic time scale t1 associated with it. At this point it hits an extremum, so it's increasing value, but then the damping begins to overtake it, and after that it turns around, and then it's a it's a steep fall after that, and then after that it's a monotonically decreasing function, which just goes to eventually the particle settles down to its equilibrium position at t equal to infinity. Then there is a third possibility, which is if it goes in the other direction, right? So if the mass may actually go below the equilibrium position or go in the other direction, right, so of the equilibrium position. So this happens when typically the direction of motion at the initial point is in the opposite direction of of the previous case, yeah, right? So there is enough velocity in it that it can actually shoot past the equilibrium point, but then damping takes over, and then it has to make a turn, and then there is a minimum here in this case, and after that it will keep on heading towards the equilibrium position. Now it comes in from the opposite direction, and then eventually it goes to zero. So but it's only one time, right? It can never there is not enough energy in it for it to perform even one oscillation, right? So that's the critically damped case, and the over damped case is basically the same, but it's a more exaggerated version of it, in the sense that damping is like really dominant here, and so there is no question of even if you slightly decrease the damping, your motion is not going to be periodic in nature, right? So that's what is different here, and so the nature of the solution is also slightly different here. So you have a times e to the minus lambda t plus b times e to the minus mu t, right? So it's not like it's not a plus bt like here, but you will have a times e to the minus lambda t plus b times e to the minus mu t, right? So right, we recall how if you have repeated roots, we have to put in an onsorts of this kind, t times e to the minus bt comes in here because of the repeated root, right? So you have to find these two independent solutions, and so whereas here both of these are you just work with e to the minus lambda t and e to the minus mu t, so that's your particular solution, and then you get your general solution by attaching these two different kinds of independent solutions. Now once again, the qualitative nature of these solutions, there are three different possibilities. So I will just show you some plots where I just played with the parameters, and I'm able to generate these three different kinds of motion. Okay, so that's all for this lecture. We discussed what happens to a vibrating mechanical system in the absence of damping, in the presence of damping, and when there is damping, depending upon the value of the damping, you may get three different kinds of possibilities. The critically damped and over damped case, each of them are of a very similar nature when there are all oscillations in the system are completely washed out. So that's all for this lecture. Thank you.